Hey, all dear friends, in this video I am going to talk about the equations of motion of a fluid flow. We know that in particle dynamics, Newton's laws of motion are F naught is equal to ma. Obviously, that is for the when the mass is constant. We want to apply this F naught is equal to ma in fluid flow. In fluid flow, when we apply any equation and that we apply along a streamline. So suppose along a streamline S, I want to write this equation F naught is equal to ma. So along that streamline S, that equation will become F naught along S is equal to mass into acceleration along S. So to apply and to arrive at the equation of motion for a fluid flow, we need to know what are the forces acting on a fluid in motion. So in fluid flow, following forces are present. First is obviously the force of gravity, and that is Fg, and then because of the pressure force, there is a force due to pressure. And if the fluid is viscous, non-ideal, so there is a force due to viscosity Fv, and then there is a forces due to turbulence. So in the LHS, in the F naught is the sum of Fg, Fp, Fv and Ft. Now depending on what are the forces present, if all the four forces are present, then the equation that we arrive is, that is the Reynolds equation of motion. If the first three forces are present, there is no turbulence force, there is a force of gravity, force is pressure, force due to viscosity, then equation of motion that we arrive for fluid flow is called Navier-Stokes equation. And if there are only two forces, force of gravity, force of pressure are present, and that will be in the case of an ideal fluid, in that case the equation of fluid flow is called Euler's equation of motion, and that is the agenda of this video. So in this video, basically I want to derive Euler's equation of motion, and simple application of the Euler's equation of motion, and based on that result that we'll get, I'll take a JEE advanced question from 2022 to see how this equation is working. So let's go to the next page. So what is Euler's equation of motion? As I said, that if in a fluid flow, the only two forces acting, that is the force of gravity and the force due to pressure, then equation of motion that will come out will be the Euler's equation of motion. And if there are only two forces, gravity, pressure, so then the fluid is the ideal fluid, because in non-ideal fluid obviously there will be some viscosity and there will also be turbulence. So to derive the equation of motion for the Euler's equation of motion, suppose I have this streamline and the fluid is flow. This is if I'm taking a streamline flow, so obviously the flow is steady, so there is no there cannot be any turbulence. So on this streamline, I am taking very small part of fluid element, and this is a very enlarged version of that thing. This is a very enlarged part, but this is a very small part of the fluid that is flowing along the streamline. So suppose the fluid that I have shown has a length ds, and this element is making an angle theta with the horizontal, as you can see. The height of this element from this end to this end is this is a very small element, suppose this height is dz. So obviously you can see that this is ds, this is dz, this is theta, so dz is equal to ds sine theta. That's number one. And the density of the liquid on this part is rho. The liquid need not be liquid, it is just a fluid. The density of the fluid on this very tiny part is rho. It can be different on this part because I am not committed that the fluid has to be incompressible. It can be compressible, so it means the density at the different part can be different. So on this little part, density is rho, and the pressure on this end is P, and pressure at this end is P plus Tp. And the area of cross section of the section shown as a dA. So now the mass of this section, this volume of this part is the ds into dA, and density is rho, so the mass is rho dA into ds. And this part, through this part, the fluid is flowing with velocity v, and the acceleration of this section is a. So relationship between a and v is a is equal to v dv by ds, and mass of this part we have written. So the weight of this part will be dmg. Want to take the component of this weight along the streamline and normal to the streamline. So component along the streamline will be that obviously dmg sine theta, and then there will be two more forces, the force due to pressure at this section and the force due to pressure at this section. So this force will be obviously P into dA, and this force will be P plus dP into the area dm. So all the thing done, we have shown the forces, we have written the acceleration. We have to just apply F naught is equal to ma along this streamline for this little element that we have shown. So applying F net along S is equal to ma along S. So taking this direction as a positive in which the fluid is flowing. So net forces, first force is a P dA, and then minus P plus dP dA, and then minus dmg sine theta. So F net is this thing, and that is a dm, that is a mass, into acceleration v dv by ds. Let's simplify this thing. This P dA and P dA will get cancelled. So the next expression we will get minus dP dA minus dmg sine theta is equal to dmv dv by ds. And now put the value of dm. The value of dm here is rho dA ds. So I've just put the value of dm here, and now what you can see that this dA will get cancelled, and obviously this ds will also get cancelled. So then we'll get one more thing, this ds into sine theta I'm going to write as a dz, that is the difference of height between the two ends. And now simplifying this thing. So simplifying this thing, I have taken this on that side, so that is a plus dA, and this will be a rho g ds sine theta is dz, that is a rho g dz, and this is obviously rho v dv. So this we've got. And now I just divide this expression on by rho. So we will get dP by rho plus g dz plus v dv is equal to 0. And this is what is known as the Euler's equation of motion. So we derive the Euler's equation of motion very easy. This Euler's equation of motion is dP by rho plus g dz plus v dv is equal to 0. And now using this relation, we can derive the Bernoulli's equation from Euler's equation. So for the Bernoulli equation of motion, the assumption is that the fluid is ideal, means there's no viscosity. The flow is steady. The flow is steady, only then we can talk about the streamline. So we write the Bernoulli's equation along a streamline. Flow is steady. Flow is irrotational, means that is not curling, like there is no vortex is being formed, and there is no the flow is incompressible. That is one important thing. The flow is incompressible. If the flow is incompressible, what does that mean? That the rho is constant, mean density of the fluid is constant. You cannot compress, mean the volume cannot be changed for a given mass. So now it is a straightforward method to derive the Bernoulli's equation from Euler's equation. So how we can get that? So this is the Euler's equation, just we need to integrate this equation. So integrate this thing. So if we integrate this thing, obviously a constant will come on the right side, and because rho is constant, so here one thing I missed here it should not be P by dP, it is actually dP by rho. So dP by rho is a constant, and we are also assuming that we are not going far away from Earth's surface, so G is constant. So integrating this thing, will get simply P by rho, and that will be Gz, and that will be V square by 2. So this is P by rho plus G by Gz plus V square by 2 is constant. And if I divide this multiply the whole equation by rho, so we'll get another form that we'll mostly use for the IIT-JEE, that like P plus rho G Z plus half rho V square is a constant, that P is the pressure energy per unit volume, rho Gz is equal to potential per unit volume, half rho V square is equal to kinetic energy per unit volume. And the meaning of that thing, that between any 2 points, if you go from there, the sum of pressure energy, kinetic energy, potentially per unit volume is a constant. So that's what we have derived. But now I want to go back to that Euler's equation, and using this Euler equation I want to derive a very important result, basically for incompressible fluid flow. And we want to derive result in case that the fluid is also following polytropic process law. So polytropic process, those who have studied thermodynamics would be very much aware that what is a polytropic process. When we write polytropic process, that is a means to express so many processes in one single equation. So in polytropic process, we assign a polytropic index, and just by varying that index, we can practically have a infinite process through that. So the polytropic process for a closed system, the equation is PV power K is equal to constant. This P is obviously pressure, V is the volume, and K is that polytropic index. In some book that K is written to be eta. So, but here I have written the polytropic index as a K, and C is a constant. But this is for a closed system. I want to write for an open system. If the system is open, so for the open system, mass is not defined. So what we do, we write in terms of density. So density is obviously mass upon volume. Mass for a given part is a constant, so we take for a given mass. So this V is kind of inversely proportional to density. Density I write with rho. So polytropic process equation for an open system will take this form: P is equal to C into density power K. Rho is the density, K is that polytropic constant. And now we'll derive the Euler's equation for this polytropic fluid flow. We will also need that rho in terms of P. So if I want to write rho in terms of P, that will be rho is equal to P by C power 1 by K. So this P is equal to C rho power K, and rho is equal to, we want to write rho in terms of pressure, so that will be rho is equal to P by C power 1 by K. And Euler's equation of motion is integration of here also it should be dp by p integration plus integration of g dz plus integration of v dv is a constant. So these two integration are straightforward. This integration will become gz, and that will be v square by 2. But here rho is some function of p, so I want to evaluate this integration separately. So to do that, let me first get this integration of dp by rho. So now let me put the value of rho here. The value of rho, if I'll put here, that will be dp upon p by c power 1 by k. That c power 1 by k go to numerator, and this will simplify to become p power minus 1 by k. Apply the normal, the power rule. So c power 1 by k, that will be p power 1 minus 1 by k divided by 1 minus 1 by k, like this. And then what I will do, I will put the value of c from here. The c is p by rho power k. So putting the value of c from here, p upon rho power k, and then power 1 by k, and this is a p 1 minus 1 by k upon 1 minus 1 by k. So that thing will become this rho power k power 1 by k, so that will be just rho, and this is p power 1 by k into p power 1 minus 1 by k, that will be p power 1 by k plus 1 minus 1 by k, that will be just p. So simplifying, that will be, and this will be simplified to k upon k minus 1, and this will become p, and this will become rho. So this integration is going to come out to be k upon k minus 1 into p by rho. So now just put the value of this integration here. value of this integration here. So we are going to get the Euler's equation of motion now for a polytropic fluid flow in a open system becomes k upon k minus 1 into p by rho plus gz plus v square by 2 is equal to constant. So this is what in IIT-JEE in 2022 a question was asked in which we had to use this equation, because an Bernoulli equation is valid only when the density is constant. So that's why I have derived that whole thing, and now I will use this equation to solve the question asked in JEE Advanced 2022. Well, let's go. So this is the question of JEE Advanced 2022 paper 1. You can see here. Most of you, I think, those who are watching my video would have definitely have given an attempt to this question. So if you're not given attempt, so please attempt it and then come back to this video. So what is written here? Let me explain. So this is a kind of a chimney. This chimney has a height h, and on this chimney at this end, this has a section of area A1, and this has a section area A2. A1, A2 are given in the question. A1 is 0.1 meter square, A2 is 0.4 meter square. And at this end, fluid ideal gas of density at the lower end 0.2 kg per meter cube enters. And it enters and at the rate of 0.8 kg per second. That is the mass flux. I mean, the mass is entering in every second. The 0.8 kg mass is entering in every 1 second at this end. And at this lower end, the pressure is given 600 pascal and temperature is given to be 300 pascal. At the upper end, temperature is given to be 150 Kelvin. The chimney is heat insulated. What does that mean? That the gas undergoes adiabatic expansion. G we have to take 10 meter per second square. Gamma for that process we have to take 2, and then we have to find so many things like pressure at the upper end, temperature at the upper end is given 150, height, the velocities at the two ends, and the density at the upper end. So we have to find so many things. So everything is written here, whatever is given, whatever information is given and whatever information is asked, that is in question mark. So the gas that is flowing through this chimney is following the adiabatic process. And for the polytropic process, for the open system, the P is equal to C rho power K, that K is the polytropic exponent. And if the process is adiabatic, the polytropic exponent becomes the gamma, the adiabatic constant, the Cp by Cv. So for this process, that P is equal to C rho power gamma, and gamma was given to be 2, so that will be P is equal to rho C rho power 2. So I will start with the thing that is given here. So what is given here? Temperature on both sides were given. Density is given here, density is not known here. So I will write with the relation between T and rho. So for the open system, again I can write P is equal to rho RT by M. Rho is the density, R is the universal gas constant, T is the absolute temperature, M is the molar mass. So just want to put P on this equation. So if I put P here, that will become rho RT by M is equal to C rho square. So this RT by M and C is all constant. This 1 rho and 1 rho will get cancelled. So basically what I am going to get, T is equal to some, let me write say that K I don't want to write, some C dash, another constant, into rho. So basically temperature is directly proportional to a density. So rho 2 by rho 1 is equal to T2 by T1. T2 is 150. T1 is how much? 300. So that is half. So density will become half. Rho 2 will be half of rho 1. Rho 1 is 0.2 by 2. So that rho 1 will be 0.1 kg per meter. In one of the option the density was, I will check all the options at once. And using this thing I can calculate that P2 also. So now I will use this equation again. P is proportional to rho. So P2 by P1 is equal to rho 2 by rho 1 square. The rho 2 is 0.1 and rho 1 is 0.2. So that will be 1 by 4. So this pressure will be 1/4 of the initial pressure. The initial pressure is 600. So P1 will be, P2 will be 150 Pascal. And now the velocity part. Velocity at the two ends. For that thing, we'll use the continuity equation. Continuity equation says dm by dt, that is the mass flux, is a constant. So mass flux at the lower end is a rho1 a1 v1, and at the upper end that will be a rho2 a2 v2, and that mass flux is given to be 0.8 kg per meter cube. So using this thing first, v1, so v1 is equal to 0.8 divide by rho 1, divide by rho 1 is 0.2, and divide by a1 is 0.1. So how much will be that? That will be 40 meter per second. Simple. And the same way we can find v2. V2 will be 0.8 divided by rho 2 a2. Rho 2 how much we got? Rho 2 we got 0.1, and a2 is given 0.4. So that will be 20 meter per second. And then we had to find that height of the chimney. For that thing we need to apply the Euler's equation for this polytropic flow. So Euler's equation for polytropic flow, we had derived k upon k minus 1 p by rho plus rho z plus v square by 2 is constant, and that we want to apply at the lower end and upper end. So this thing at the lower end, that is p1 rho 1, height is say z1 and the velocity is v1. At the upper end, that will be k upon k minus 1 p2 by rho 2 plus rho z2 plus v2 square by 2, and the k was 2, k is 2, so that will be k upon k minus 1, 2 upon 2 minus 1 is 2, so this is 2. At the lower end, p1 is 600, density is 0.2, this is rho 1. Again, one minute, this is not rho z1, this is gz1, and this is gz2. At the lower end, suppose we take this height start from here, so this is 0, and the v1 is 40, so 40 square by 2, and at the upper end this k upon k minus 1 is obviously 2, p2 we had calculated to be 150, so 150 by rho 2, there rho 2 was half of the rho 1, so 0.1, and gz2, the z2 here is h, that is what we have to calculate, and the velocity we calculated there 20. So 20 square by 2. So one thing, so that will be how much? 10, 6,000, and that will be minus 3,000, and 40 square 1600 minus 20 square 400, so that will be 1200 by 2, and this is 10h. So 300, 3000 by 10, 300 plus that will be 60. So h we will 60, and that is h. That is h. So h we have obtained 360 meter. Now let's see what are the options, and let's conclude which options are correct. So the pressure of the gas at the upper end, we had calculated that to be 150, so this is wrong. Lower end velocity 40 and upper end velocity 20, that what we got, so this is correct. And this height we just calculated 360, not correct. And density at the upper end we calculated to be the half of the lower density, so that is also not correct. So only one option is correct, and that is option B. And in this option B, that could be calculated using the equation that I've derived. Those equation who use the Bernoulli equation will get the wrong answer. In fact, this answer will come if you use the normal Bernoulli equation. So, but that is wrong. So thank you for watching. Stay tuned for such videos, especially for JEE Advanced and Olympiads.